Okay, so I can see multiple people have joined. And so am I audible, loud and clear?
Yes, sir. Good evening.
Okay, good evening. So let us start our discussion. So welcome everyone again. This is the week third live interaction session on the course of non-conventional energy sources. The course is taken by Professor Prathap Haridoss from IIT Madras, and we are having the live discussion session. So again, as my introduction, I am Lalit Bharti. And I'm a Prime Minister Research Fellow in the Department of Physics at IIT Kharagpur. And this is my email and my LinkedIn profile. So if you have any queries, any question regarding to the course or anything related to this, so you are free to contact me. So today we will be covering the week three week three course content of week three from your syllabus. So up to week three, you might have gone through the main lecture classes. So the idea here is we will just revise the week three content quickly, and then we will go to the assignments which are related to your main exams or based on your previous year assignment or your previous week assignments. So we will go through these. So let us start with the revising the course content. So I guess,
Sir, one thing I would like to ask,
yeah, sure.
uh, when anyone teaching on Zooms, no, so we will take the screenshot of some important topics because we have discussed. But we are unable to take a screenshot in case of Microsoft. So it was disabled by you, yeah, this is a feature of Microsoft.
No, from my side, you are free to take the screenshots, but I guess maybe this is the problem with the Teams, but you should be able to take the screenshots. Otherwise, the PPT is already available. If you like to get the screenshot, but the PPTs are available on the Google Drive. So you can download those also from there. Have you got these PPTs?
No, not sir, this PPT. Only for first 10 weeks lecture.
Or which first? Sorry.
First week discussion.
If but first week discussion also the video and the PPT is available. Video is available on YouTube and the PPT is uploaded on the link. I think you should have the link for the PPTs. Every week, whenever we do the discussion, we just upload the PPT on the on next day or the similar day.
Okay, sir. Okay, sir. Thank you, sir.
So you can find it. So you don't need to the go to and take the screenshot in that case. So lecture 6 and 7 seem similar. So this is the PDF version of what notes you have available online, which you can download from the course instructor. So I'm just quickly going through and we will just revise and we'll try to solve the assignments in that case. So this the topics here is energy consumption. So learning objectives are to become aware of the consumption pattern of energy across sectors and to become aware of energy users across nations and their population, because we need to understand the pattern of energy consumption across sector wise as well as across nation wise and according to their population. Then we will know where we need more energy and why we need more renewable or more clean, green and clean energy. So I guess some of the part was already covered in previous class. Okay, this was done. This was done. Okay. Consumption up to here, the classification of energy was discussed in previous class. So we need to start from consequences of energy consumption. So here the learning objectives are to become aware of the link between energy users and development. Here development means the development or of the entire nation, and to become the aware of the impact of energy users on the environment. So we'll just try to link the development of a nation of uh, a particular nation to energy consumed by them. So you can see this is data for India, a relation between GDP and energy uses. So you can see one graph is, let's say the blue one is the units are not mentioned here, but the let's say the blue one is for the GDP and the red one is for the energy users in exajoules or some relevant units. So as you go from 1985 to 2010, so you see clearly there we have a significant increase in GDP. So as the nation is growing, your energy usage is clearly increasing by that. So we can also understand if we have more development, we have more electronic gadgets, we have more industries, we have more roads, transport, and many other electricity consuming uh, appliances, then the energy uses by us will increase. So this is the trend shown in up to 10, and you can guess that after 2010 we have our GDP has also significantly changed. So energy uses is also increased significantly after 2010. So this is just the example of is just some data of five highest state GDPs in India. So Maharashtra has the highest GDP, state GDP of uh, out of these five. Then comes Uttar Pradesh, then Tamil Nadu, Karnataka, and Gujarat. And this is the power install allocated in first time in western region, northern region, southern region. So this is just to compare the state-wise GDP or state-wise energy consumption. Uh, So here we can see the some states where lower power install allocated. So we can see that Arunachal Pradesh, Manipur, Nagaland, Mizoram. So the north, basically northeastern states. So these are using less power than the states having high GDP, high state GDPs. So that is clear from our understanding that if we some state have more industries, more population, more growth leads to higher GDP, higher gross state GDP, then the power installed and power consumed will be higher compared to the states where industries are or the energy consumption is less. So this is the link between atmospheric CO2 concentration derived from in situ air measurements. So for, let's say, for example, for a observatory in Hawaii. So you can see from 1960 to 2020, the atmospheric CO2 concentration is also significantly increased from 320 ppm to 400 ppm. So that is also directly related to your GDP. Your GDP will increase the energy consumption, and we know the for most of the energy is consumed by non-renewable energy sources, so it will produce excess CO2 in environment. So the environmental CO2 levels are increasing significantly by the time. So energy usage is a present form in changing environment is a never seen before manner. So we can clearly see from the previous graph also that from recent few years only the CO2 levels are getting very getting even going from around 300 to 400. So this is a very significant change in environment. So yes, our energy usage is really impacting the environment, and we really need to move towards non-renewable or clean energy system. So this is also example in terms of global land ocean temperature anomalies. So we can see the temperature changes, the temperatures by year, these are increasing significantly from, let's say, 1960. So from 80 to 1960 there's some increase, but from 1960 to 2022 to 2020 this is significantly increasing. So it is also an example of climate change or the global environmental change due to the energy usage or due to the development of world, or you can say of humanity. So this is the data from NASA. So this is also a very good significant example of impact on environment. So this is the 10 warmest year globally based on the temperature anomalies. So you can see the time 10 time it is on the scale of 1. So it is also increasing by time. So the x-axis is not visible here, but this is also showing the temperature is increasing or the warmest day is increasing globally by the time, by the year. So it is, these are some examples. So these were showing the development, the link between development of world or development of nation to energy uses. So we know that we can understand, we can conclude that the energy consumption or energy uses have significant if impact on present on the environment at the present time, and it will uh, even more be impactful in the future. So this was the effect of energy consumption. So now we have come to our next topic, which is solar energy. So basically, from this chapter or from this slide, we are starting our uh, detailed studies of renewable energy sources. So we know the first renewable energy sources is solar energy. So we'll start, and first we will understand the from sun to earth transaction, how it happens from in form of solar light. So learning objectives for this chapter is to calculate the energy received by the Earth from the Sun, and to compare the energy received by Earth from Sun with the energy used by humankind. So we'll try to calculate these quantities. So here an example is given. The surface of Sun is around 5,500 degrees Celsius, and core is several million degrees Celsius. So how much energy Sun radiates, it is calculated here. So in this calculation, sun gives out around 384 iota watts of energy. So it is 384 times into 10 to the power 24 watts. So it is a huge amount of energy. We have already we have already studied the quantities, so the units of power. So this kind of power is huge, and so this is the total radiated energy, not received by the Earth. It is the total radiated energy by Sun. So we'll try to calculate how much power do we get on the Earth. So let's say this is shown that this is your Earth. Okay, so this is the blue color is the Earth. Its radius is around 3,400 kilometers, and the yellow color is the Sun, which have the radius of 0.7 million kilometers. And we have the radius of the orbit, or you can say the distance between Sun and Earth is around 150, or precise 149 million kilometers. And we know that power radiated by Sun is 384 iota watts. So by using this radial orbit and surface area of Sun and surface area of Earth, we will calculate the total power emitted versus total power gained or received by Earth. So this is the intensity of Earth's intensity of Sun's radiation at Earth orbit. So 3.84 into 10 to the 26. This is the total power. Then 4 pi r square. So r will be the radius or the distance between Sun and Earth. So it is around 1377 watt per meter square. So this is total uh, in per meter square radiated by Sun. Then we will calculate the area of Earth disk. Let's say this is Earth, and the area will be the radius is 6,400 kilometers. So calculate from here. So it is around 1.27 into 10 to the power 14 meter square. So this area of this disk, this is in range of 10 to the power 14 meter square. Then power
Please.
received by received from the Sun by Earth, then we'll multiply this and we'll get around 1.7 into 10 to the power 17 watt, or in joule per second. So this is the power received from the Sun by Earth. So you need to just mindful about these numbers. Then we have calculated the energy received from the Sun by Earth each year. So this was the power. Then from we will convert from power or in watt to energy in joules. So this is, if you say this is joule per second. So if you calculate in year, then you multiply just from second, you make it in minute. From minute, you make it in hour. From hour, you make it in uh, days for multiplying by 24. And then for per year, you will multiply with 365 days. So the total energy comes out to be 5.5 into 10 to the power 24, or 5.5 million exajoules per year. So why we are doing these calculations? So we try to understand that how much energy we can get by the solar energy from Sun. So this is a rough calculation of how much, and so it is very huge energy, 5.5 million exajoules per year we can get. But we need to see how much energy we can harness to run our devices. So this is the total energy we get or we receive from Sun. Then this is the example, sorry, this is the comparison from our previous classes. This how much energy do humankind uses. So whole world use 500 exajoules per year. So just try to compare 500 exajoules we need, but Earth receive 5.5 million exajoules. So 500 and 5.5 million. So it is already very high compared to the humankind requirement. So this energy received, if you try to divide, so you will see that only 0.033 days or 0.79 hours is enough for a year's humankind energy requirement. So this is the calculation to show that how much energy do we receive from sun. So you can clearly see it is uh, on the magnitude of a million exajoules. So it is very high compared to our requirement. So it is 0.79 or let's say around 1 hour. So the statement clearly says this is 0.79, but okay. So 0.79 hours is for the ideal case, but do we know that not all energy can be harnessed? So let's say only 30%, 30% is reflected back. So we are using only 70% of energy. So the 70% is, if we divide by 70%, so this 0.79 goes around 1 hour. So the energy used by humankind each year is received in 1 hour only. So this 1 hour is important. So it is also asked in previous questions that how much time we really need if we try to compare the whole solar energy received by Earth to light up or to fulfill the requirement of humankind. So this comes out to be 1 hour approximately. So this is also some calculations. What is Dyson sphere? Then first the Freeman Dyson has defined or just explained this method to how much all energy received by planet, then energy by star, by galaxy. So it is in detail, it is taught by a professor in charge in main lectures. So you can also go there and you can see, you can learn in details. So conclusion from these slides or this chapter is Earth receives nearly 5.5 million exajoules of energy from the suns each year, and the entire energy used by humankind each year is received on the surface of the Earth from the sun is each hour. So each hour, this is to compare the magnitude of energy required versus magnitude of energy received by the solar. So this was the first, just the introduction of quantification of solar energy we received and we require. Then the solar budget. So again, I am just briefly explaining you few more points covered in previous slides. So in this, our learning objectives will be to know how incoming solar energy is distributed across various phenomena on Earth. So we'll see the solar energy is not uniformly distributed, or the distribution of solar energy. So how it affected by Earth's surface or Earth's structure. Then to become aware of geographical and seasonal aspects. So we'll see if the solar energy is equally available in all seasons or in all areas of Earth, or it has some relation. Then to become aware of impact of time of the day on the availability of receiving solar energy. So we in simple manner we know that the sunlight intensity will be higher in the peak afternoon, then it will come down. So the similar kind of studies we will do in these slides. So these are the layers of atmosphere. We have already discussed that the troposphere is the lowest or the closest layer of atmosphere from the Earth's surface. So up to 10 to 12 kilometers, the troposphere is there. And most of the human activities and happens in the troposphere, including your weather, including your aviation, and including we living on the Earth. So these all these activities comes in the first layer of atmosphere, which is troposphere. Then we go as we go higher, we go into the stratosphere, mesosphere, thermosphere, at the end, exosphere. So the statement is approximately 80% of mass of Earth's atmosphere in the troposphere. So 80% comes the mass of the total atmosphere, it comes in the troposphere, because as we go away we know that density will decrease and mass will decrease with the height. So most of the activities and most of the mass is included in the troposphere only. Then this was the previous example, the calculation. Okay, so this is good to understand that in a daylight, how much power 175 picowatt, or let's say this is how much 1.7 times power 17 watts we are getting from the sun. So this is the distribution, how much energy do we really get by at the Earth's surface. So 6% is all at the first reflected by the atmosphere. Then 16% reflected. Then 16% is absorbed by the atmosphere. So this that will be used to warm up the atmosphere and increase the temperature of the atmosphere around us. Then comes to 20% will be reflected by clouds. 3% will be absorbed by the clouds. So this will again be used to increase the temperature. Then 4% will be reflected by the surface, and 45% of that will be used to rising air cloud formation radiation absorbed by the atmosphere. So this that will also absorbed by the atmosphere. So you can see 6, 16, 20, and 4, and that much is and 3% this much is used before reaching the Earth's surface. Then 51% is absorbed by land and water. So this is the power used by the Earth's surface to warm up the surface or the land water. Then 64% radiation of the space, atmosphere, and cloud. So this is in the night case, it is radiated back, and 6% directly radiated back by the Earth space, by the Earth to space. So this is a simple comparison. Then this slide is not properly visible. So from this, we can conclude that solar energy is absorbed and released through a wide range of phenomena on Earth, and geographical location and seasons are important aspects of impacting solar energy received by the specific location. And the time of the day is also important. So from here also we can understand that the sunlight comes directly at this region, and we know that we are as living in India, we are living in the middle of the earth, and so this region gets very much of the very much contribution of the total power from the sun, and the poles in comparison gets a very uh, in comparison gets a lower energy, and that's why the poles are remains cold all in all the weathers. So we can say that yes, most of the energy, most of the solar energy is received at this center of the earth. So these areas are pretty much utilized for solar energy generation compared to the poles or uh, the poles of the earth. So these are some more slides on the electromagnetic radiation, the solar spectrum. So this is again taught well in details by the professor in charge. So we'll just go through it just to solve our assignments. Otherwise, you can go to the main lectures for detailed understanding. So just learning objectives for these are just the features of electromagnetic radiations, just to understand the electromagnetic radiation. Then the features of solar energy spectrum. So how many radiations type of sorry, how many wavelengths are included in the solar spectrum? So this kind of things are explained, and the ability of plants to capture the visible spectrum. So this is the example of black body radiation. So this is also part of your class. So it is just compared that the lower the wavelength, the higher the temperature will be of the most intense part of the spectrum. And the as temperature of the body increases, intensity of the radiation from the bodies also increases. So if you are not aware of what is Kirchhoff, this black body design, so it is basically a black body is considered as the perfect absorber of radiation or light. So it is made of a black colored material which can absorb light of all color or the whole spectrum from the sun. So and we have only one point where the light can be incident and can go inside the black body, and when hitting the surface, it will some of the part will be absorbed by the black body and some of the part will be reflected, and as it reflects, it will reflect an incident back to some surface of the black body's this internal curvature. So by that, the by this circular design, almost all of the energy is uh, or the all of the light waves will be reflected back and either absorbed or reflected back and then consecutively absorbed by the black body. So this is example where whole spectrum can be absorbed by light, and similar thing happens when so it will the temperature will increase when the light hit the black body, and similar thing happens if you increase the temperature, if you heat it up, so it will emit the light of whole spectrum. So this is called the black body and black body radiation. So this is the curve for black body radiation. So you need to go to the full lectures to understand this, why the temperature is the peak is shifted by the increasing temperature, and value of H obtained by Planck, and why this is the current accepted values, and the comparison it is quite close, and the law of distribution it is. So you need to go through the main lectures for this. So this is the fundamental of photoelectric for the photoelectric effect. So if you are aware of this, so you have some photons with the kinetic energy of half mv square. So the h nu is the it is called the what you call it? Okay, so the slides are not complete. So what you can do, you can go through main lectures for these kind of slides. So we can start with the main assignments. The semiconductors comes in your next lecture. So up to this, we are done with these three lectures. And so we saw this total solar energy, the comparison of solar energy received and observed by the sun. And then we saw the some types of the electromagnetic spectrum of sun's radiation. So let us come back to our presentation. Okay, so this is our week 3 presentations content. So we have gone through this consequences of energy consumption, solar energy, the sun to earth transaction, then the solar energy budget. So we have multiple questions here. So these are basically our assignment questions from let's say from previous year assignments or this year's non-graded assignments. So and last week's graded assignment, so which need to be submitted, but uh, these questions can be useful for your main exams of this course. So we'll take a break of 5 minutes. So I will come back at 7:50 and then we will start the assignments part.
Okay, sir.
Okay, so we are back to our discussion. So we'll start the assignment parts of this session. So these are the assignment based on what we covered in few minutes early, few minutes back than this assignment. So we'll start with the question first. So the question says the size of the planet decides how much energy from the sun reaches the planet given in the fixed orbit. So these are non-graded assignment questions, so you may find them easy, but yeah, they come in your exam sometimes. So it is to understand the solar energy production and the receiving the solar energy. So how the solar energy generated? So basically at sun, we see the atomic fusion happens instead of, say, let me just, okay. So we know there are two types of radioactive activities, fusion and fission. So in atom bombs, we see the atomic fission where uranium or high mass atom will divide it into two parts and it will emit some energy within the difference of the mass of both of the atoms after the fission. But here what we see, we have one hydrogen here and one hydrogen here. Basically, it is the deuterium isotope and this is the tritium isotope. So they will fuse together to make helium, which is basically 2He4, which is a alpha particle. It is also known as alpha particle. So one neutron plus helium, and the mass difference will be converted in the energy by using equation of E is equal to mc square. So the total mass of the reactants is higher than the total mass of product. So we will some mass will be converted into energy. So this energy is basically the source of solar radiation on sun. So this is the total energy. So we saw in our previous slide that total energy emitted by sun is 384 yotta watts. So this is by the sun. And the question asks that does the size of the planet decide how much energy from the sun reaches to the planet? So yes, this number is not affected by the planet size, but what energy received by the planet, it depends on the what is the size of the surface or the surface area or the size of the planet. So this statement is true that yes, the size of the planet decides how much energy from the sun reaches to the planet. Then we come to the question two. So there is a close link between GDP and of a state and the power consumed by the state. So we in our previous lectures we saw that there's a clear link of GDP of a state with power consumed. So if a state is having higher GDP means it is having more productive production, more industries, more transportation, more energy extensive applications. Then the so the if the GDP is higher, the power consumed will also be higher. So this is a basic definition of what is the GDP. Then how the GDP is related. So GDP is related to the financial activities of a particular state of or a nation that is directly related to the energy. So if we see the contribution of GDP on the annual basis is one of the major contribution is from the finance sector and the manufacturing. So 15% comes from the manufacturing. So if you have more industries, more manufacturing units in a state, then the GDP will be higher. And then since the manufacturing lines, the transportation, other construction and agriculture, forestry, most of these required energy to run. So if your GDP is higher, your energy demand will be also be higher. So yes, this statement is again true. So let's say, okay, let's come to the question third. So the hypothetical Dyson sphere will capture all of the energy from the sun coming to the orbit of Earth. So we saw this term Dyson sphere in our lectures. So let us define it again. So what is a Dyson sphere? So Dyson sphere is a hypothetical megastructure that encompasses a star and capture the large percentage of its solar power. So for example, or just to understand, let's say this is a Dyson sphere. So this is a structure that can capture most of the solar radiation of of a sun or of a star, or let's say sun. So this is, if you consider the structure that will uh, encompasses all of the sun's solar energy. So whatever iota watts, the 34 iota watts, that will be received by the this sphere. So that is called the Dyson sphere. So there's no megastructures like this in real. So it is a hypothetical structure. So you can just to estimate the total energy emission by a star. So this hypothesis can be utilized. So then we come to the question 4. So it is there is a strong need to change the source of energy used by the world. So let us understand the question. The change the source of energy by using by the world. Why we are saying that? So this curve shows the world energy consumption scenarios. So from 1960 to up to 1920, it is showing the actual data. And then this is the forecasted data. So in this case, the medium population forecast, it is given in red, and the low population forecast is given in the green. So we can compare that from 5,000 to, let's say, around 15,000, we have came from around 1960 to 2020. And as we go per 10 years, we will be increasing our energy consumption with a significant amount. So let's say for 280 or 2100, we will reach around 30,000 million ton per annum, which is around double from the 2020. So in a time span of, let's say, 80 years, we will reach the from 15,000 to 35,000, which is a say very high jump in the energy consumption. So we know that from the energy consumption, this this energy is, for now, it is coming from the coal gases or the conventional or non-renewable energy sources. So basically, we are getting from the fossil fuel based energy sources, which are emitting carbon dioxide. So that is why we saw this curve earlier also. That is why our carbon dioxide emission is increasing. And from 1980 to 2020, we have got from 340 to 420 ppm in the atmospheric CO2 levels. So it is significantly increased. That is why we need to switch the sources of our energy. So that is why we need to move from traditional to non traditional and non-renewable energy sources to new clean and renewable energy sources. So that is our main motto, just to minimize the environmental impacts. So this statement is true that yes, there is a strong need to change the source of energy used by the world. So we are at the question 5. So question says the solar spectrum that reaches the surface of the Earth is impacted by gases in the atmosphere due to the wavelength that they absorb. So that is clearly yes. So we saw that the effect of our atmospheric layers. So our atmosphere, some of the part is reflected and some of the part is absorbed by the layer, atmospheric layer to warm up, and it will warm up in that case. So yes, that is impacted by the gases. So it is also shown here. So if this is sun, some of the part will be reflected directly, and some of the part will be reflected by clouds. Then some of the part will be reflected by the Earth's surface, and some will be absorbed by the atmosphere, and then by the also by the Earth's surface. So this is the explanation what is happening basically in Earth in the layers of the atmosphere. So basically what we have some gases like CO2, CH4, methane, and water is present in terms of H2O. So this will absorb the sunlight, and some of the long wavelengths radiation is not reflected and radiation into the space. And some part will be absorbed and the heated surface radiation. So these are the long waves, infrareds, energy into the atmosphere. So just the summary of this picture is here is to the sun's energy, some of this reflected and some of the absorbed by the atmosphere. And in atmosphere, we have different gases which will interact with the solar light. So this statement is true. Yes, it is the solar spectrum reaches to the surface of the earth that is impacted by the gases of in present in the atmosphere. So this is called the greenhouse effect. The gases present in the atmosphere will interact with the atmosphere with the solar spectrum. So these gases are basically methane and CO2. So that is why we need to control the level of CO2 and methane in the atmosphere, just not to having more greenhouse effect, which will increase our temperature of Earth's surface. So that is why we need to control the ppm levels of CO2 and other greenhouse active gases. So these are some questions from the previous year. So the question one, the question one is the as the GDP of a nation increases, energy consumption generally increases, decreases, remains unaffected. Initially increases, then steadily decreases. So this question is very much cleared from our previous discussion. So our GDP is directly related with the energy consumption. So that is clear that yes, if the GDP is increasing, then the energy consumption is increasing. So we have already discussed the this pie chart, this datas of GDP versus energy uses. So we already know that yes, GDP, if the GDP increases, the energy consumption will significantly increase. Then we have the statement that Maharashtra consumes more energy than Tamil Nadu. Okay, so we have this statement that Maharashtra consumes more energy than Tamil Nadu. Then we have conclusion that based on the trend usually seen in the relationship between energy consumption and economical activities, A is Maharashtra has more GSDP than Tamil Nadu, and Tamil Nadu has more industrial output than Maharashtra. So which of these follows and which does not follow? So this kind of discussion, this kind of comparison we already saw when we were comparing the states of India. So this is the Maharashtra. and this is Tamil Nadu, let's say. So it is given that energy wise, Maharashtra consumes more energy. So if this is energy, Maharashtra consumes more energy. So we know that energy consumption is directly related to the state GDP. So if the energy consumption higher, then the SGDP will higher for Maharashtra, then Tamil Nadu. So our statement 1A is correct that Maharashtra has more SGDP. If the energy consumption is higher, then GDP will also be higher. So the statement A is correct. But the statement B is saying that Tamil Nadu has more industrial output than Maharashtra. So Tamil Nadu has more industrial output than Maharashtra. But as we know, if SGDP is higher, SGDP is directly related to the industrial output. So if SGDP is higher, then the industrial output should also be higher. So these all are interlinked, the energy, SGDP, and industrial output. So the industrial output of Maharashtra should also be higher. So this statement 2 is, or the statement B is not a conclusion. So we can say that conclusion A follows, but not conclusion B. If the conclusion is given that Maharashtra has more industrial output than Tamil Nadu, then it will be correct. Otherwise, in this case, this is wrong. Then we come to the question 3. So this is based on the atmospheric CO2 level. So the question says 40,000 years ago, the atmospheric CO2 concentrations was blank, and this is determined using bubbles of blank trapped in ice. So we saw the method of how the levels in history was calculated or by measured. So from our previous studies, it is explained in your lectures that 40,000 years back, the levels of CO2 was very low. It was lower than 300 ppm. So if you go from for this trend, so at 1985, it was around 3. This is GDP. So at 1980, it was around 340. So we can expect that 40,000 year back, it will be significantly lower than 300, but not very low, because being very low, the greenhouse effect will not be there, and we will not see the formation of Earth's atmosphere and the life on Earth. So it is not more than 300 ppm. So how it was determined? So you don't have any data of 40,000 years ago, but what you can get, you can go to the poles, either on Alaska or in Northern Pole, or let's say Antarctica and Southern Pole, and you can do carbon dating of water or the ice. So what scientists have done, they have taken the ice sample and done the carbon dating on that. So they found that yes, this ice is 40,000 year old, and they try to find the air bubbles trapped in the ice. So if the ice is 40,000 year old, then the air will also be at the same time, and it will be 40,000 years ago. So then they try to estimate the CO2 levels in that trapped air samples. So then they found that it is less than 300 ppm. So this is a very intelligent way to calculate to estimate the ppm level of air, what was in the history, and a very long time scale back at around 40,000 years ago. So this was the way they have calculated it, and they found it is less than 300 ppm. Then we have again the next question on the CO2 level. So the statement says glaciers are melting due to the increasing CO2 percentage in the atmosphere. So this is the statement. The glaciers on are melting due to the increasing CO2 percentage in the atmosphere. So the conclusion is CO2 traps the energy which comes from sun, and more CO2 in atmosphere means more absorption of energy released by Earth. So we need to understand by what is a greenhouse effect. So let's say this is your greenhouse. This is your example. This schematic representation of greenhouse effect. So these are greenhouse active gases: CO2, NO2, SO2, methane, ozone. So what will happen when this solar radiation incident on Earth, and whatever the reflected solar spectrum by the Earth's surface, they will interact with these kind of gases. They will absorb the energy, and they will reflect back the uh, energy to the Earth's surface. So this cycle goes on. So whatever reflected sunlight leave the Earth's surface, they will interact with these CO2, NO2, SO2, these kind of gases, and then they will reflect back the Earth's surface to the Earth's surface. So in this process, the temperature of the Earth's surface increases. So this is again shown in a basic example. So this kind of structure are also used in farming when we use the greenhouse assisted farming. So if you need to increase the temperature, so let's say we have a cover or a film here which is semi-transparent to Earth's sunlight. So sunlight will directly, the high intensity sunlight will directly penetrate through it and go to the chamber. Then whatever will be the reflected light, that will reflect back to the surface, the ground, and that it will interact with this transparent film. So since this transparent film is not, it will interact with it, and it is, since it is not perfectly transparent, it will reflect back the major portion of the reflected light. So in this case, or in these cycles, multiple times the sunlight will reflect back to the ground or the surface. So the temperature will increase. So this is also shown here. So the statement A is correct. The CO2 traps the energy which comes from the sun and sent back to Earth. The statement A is correct. And more CO2 in the atmosphere means more absorption and more released in this Earth surface. So this kind of gases increases, then we will see more greenhouse effect. So that is also obvious that statement B is also correct. So that is why we have the issues of CO2 levels, and the NO2 is also a major pollutant which is uh, affecting the Earth's global temperature, and we need to minimize the NO2 levels, CO2 levels in the Earth in the atmosphere. Then this questions comes from the our previous calculation. So this is again the same calculation we did in our previous slides. So
Am I audible, sir? One query.
yes, sir, sure.
Please go to the previous slide, sir. Question regarding question.
Hmm.
सर आपने इसमें कहा ना कि जो है सनलाइट आ रहा है अर्थ पे और अर्थ से रिफ्लेक्ट हो रहा है, फिर वो CO2 एब्जॉर्ब कर रहा है। जब सनलाइट जब अर्थ पे आ रहा है तो उस आते वक्त में भी तो CO2 एब्जॉर्ब करेगा जो गैसेस हैं एटमॉस्फेयर में।
यस, सो जैसा कि हम इस
कि
एग्जांपल में देखेंगे।
रिफ्लेक्ट हो रहा है तब जाके एब्जॉर्ब हो रहा है गैस के द्वारा। जी जी।
So ये actually these kind of molecules are, let's say these are called IR active molecules. So इनमें क्या होता है, ये एक बार सनलाइट से इंटरेक्ट करते हैं और उसको एनर्जी एब्जॉर्ब करेंगे, एंड देन ये वाइब्रेट करेंगे, एंड देन दे एमिट बैक द एनर्जी. So if you see here, the radiated heat. Okay, so you can just understand from here also. So at the first also they will absorb some energy, but that will be used to increase the temperature of atmosphere. और जो ये reflect back हो रहा है, so let's say how many percentage I don't know exactly. Let's say 15% or 16% should be reflect back. So जो CO2 है ये एक layer बना देगा. So what this layer will do, it will reflect back this reflected radiation. So which radiation should be reflected to the blank space? So major portion will reflect back to the earth. So this is a cycle. So yes, at the initial also they will absorb some energy, but this cycle plays a main role. So it will increase the temperature by many degrees. So similar example we see in the greenhouse farming. So what happens? Let's say you have a place where temperature is let's say 15 degrees only, or around 10 degrees in winters or in some day. So, but for farming of some specific plant, we need temperature around 20. So this kind of greenhouse agriculture thing, so it will increase the temperature by few degrees. So it will significantly improve the temperature. So it happens this in the same way. The if you have this transparent film, so the sunlight will interact. Yes, the transparent film will get heated. So that is true. But the main phenomena is happening in this cycle where it is consequently continuously reflecting back to the surface. So then in this case, the chamber will get heated. So similarly, the earth is a chamber here. So if you have this kind of film, so this cycle will reflect back multiple times the radiation, and the radiation will not uh, leave the earth's surface. So that is why the temperature is increased in the at the sun, at the earth surface. So I guess you this is clear.
Yes, sir. Thank you, sir.
So if you have any queries, you can just stop me anywhere and you can ask me anytime. So this is again the same calculation. The world's total energy used in this is the same as the energy received by sun in what time? So 10 hours, 0.042 days, zero point 0.1 hour. So we clearly calculated from the distance between sun and earth, then how much power we are getting at the sun's at the earth's surface, then power in terms of watt or per joule per second, then per year how much we are getting, per day how much we are getting. Then we calculated that yes, if the efficiency is 70%, then we will get it in 1 hour. So we calculated it back in the previous slides. So 1 hour or 1 hour is equal to 0.042 days. So both options are correct. 0.042 days or 1 hour. Then the sixth question comes, the what are the various options possible to maximize energy received by a planet from its star? So for example, we have sun and we have earth. So what can be the possible ways? First is increasing the surface area exposure of the planet. So yes, that is correct. If your surface area is higher or the planet is larger in size, the energy received will be higher by the planet. Then bringing the planet closer to the sun, to the star, that is also correct. If you come close to sun, because the sun emits energy radially outward, so as close you are, the energy received will be higher. Using the Dyson sphere method. So what is the Dyson sphere? We saw that Dyson sphere is a hypothetical megastructure that encloses all of the star's energy. So this dashed line can be considered as a hypothetical Dyson sphere. So that is the way to maximize the energy received by the planet. So in this case, by the sphere of the Dyson by the Dyson sphere. So that is also correct. And the fourth option, moving the planet further away from the star. So that is clearly contradicting our second option. As you go far, your energy received will be lower. So the option 4 is incorrect, but all three are correct. Then this is the question on the okay. The temperature of the sun's surface is approximately how much? So again, Earth's surface, we know this is due to the fusion, and we saw that it goes around 5,500 degrees Celsius at the surface of the sun. So it is around 5,500 degrees Celsius. And the option asks so similar in order of magnitude to the temperature attained during arc welding. So we need to see that how much temperature is required for the arc welding. So this is an example of arc welding. And if we see the temperatures in this area, so this is the thermal profile of arc weldings, and the maximum at the maximum velocity zone, the temperatures are around in the 1600 or 1600 1500 Kelvin at this range. So it is around near to 1000 degrees Celsius. So it is the magnitude is similar. Let's say 10 power 3 and 10 power 3 here. So they are just asking about the magnitude, not the exact numbers. So that is why the question, the option third is also correct. Then we come to our eighth question. So that says arrange the following in their increasing order. So A is radius of Earth's orbit, Earth's radius, and Sun's radius. So that is clear that this orbit is the highest in radius. This is the Sun's radius is second, and Earth radius is at the third. So we know the numbers and we can clearly see the order. So the option one is clearly correct here. That largest is the radius of Earth's orbit. So this is the orbit, then Sun's radius, then the Earth radius. So option one is clearly correct. Then we come to the ninth question, which says at a given point of time, one side of Earth radius energy obtained from the sun back to the space because at this given point of time, one side of Earth radiates energy obtained from the sun back to the space. So this is a typical example of a day where this is the sun and the right side is the earth, and at the half of the approximately half the portion we can see it is day and it is night. So clearly the solar spectrum is absorbed by the earth and the temperature increases, and at the night time, since the temperature is higher, then the radiation is emitted by from earth to the vacuum for the space. So the temperature in night is still higher than the temperature of vacuum. So it will radiate the energy. So if we see our options, it is night on that side of Earth. So yes, there is night at this side. The temperature of that side of Earth is more than that of the dark side of the space. So yes, the temperature is higher than the dark side. Then the third option is the surface temperature of the other star is less than of the sun. So that option is not correct because the temperature of star doesn't change. The TS will remain same. And the option four is moon is hotter than the sun. So that is not relevant because moon has no effect on this phenomena. So the only option is because we have the night at this side, but we have the temperatures of Earth higher than the temperature of space, then we get this phenomena. So option one and two is correct. The 10th question is The intensity of sunlight incident on Earth is higher during the blank of the day, and therefore a solar device capture blank light during that part of the day. So we clearly know that intensity will be high at the middle of the day and more in the morning, low in the morning and evening. So that is clearly known that the intensity of sunlight is high in the middle of the day. So middle will come here and morning will come here. And so intensity will be higher during the middle of the day than morning of the day. And whatever solar devices we use, we capture more light during the part of the day. So option 1 and option 4 is correct. Both morning and evening option can come here. Then we have the previous quiz question. So we have 5 more question, I guess. Okay, we have multiple. So we'll go quickly now because these are questions from previous quiz also. So we'll just go fast. So this is the question related to GDP versus the energy consumption. So a GDP of a nation was $1 trillion in 15 and it increased $2 trillion in 2020. So what can be the correct options? The oil consumption decreased in the nation. So no, that is not correct. If the GDP is increasing, the oil consumption will also be increased. The energy consumption of the nation increased. Yes, that is correct. Life expectancy in the nation decreased. So that is not correct because if your GDP is increasing, your nation is developing, then your life expectancy will also should increase, not decrease. So the option third is incorrect. And fourth, the goods and services totaling to the greater value of being produced in the nation. So they will be total in the greater value than the previous year because your GDP is increasing by time. So option 2 and 4 are correct. Then we come to the question 4, which combines of energy resources is more useful to us for long term. So which energy sources we need to require, which combination we need. So for now, we have the conventional sources, which is coal, oil, petroleum, which is having the issues of carbon dioxide emission. So we need renewable and non-conventional sources. So in the option, if you see, we don't need the coal, we need clean energy, renewable and non-conventional. So basically renewable and non-conventional comes in a similar domain. So option 2 and 3 are correct. And fourth is non-conventional with cheap oil. So we don't need oil or coal. We just need the clean and renewable energy sources. So option 2 and 3 are correct. Then we comes to the wind and solar energy are first renewable energy sources. So yes, that is clear that renewable means they will not finish in human life scale. So solar is always available, wind is always available. So these are renewable. They are very clean compared to other sources and intermittent in nature. So what does it mean by intermittent? Intermittent means the it is a nature of the energy sources means when you have the okay, let me read it. Energy that is not continuously available due to the external forces that cannot be controlled and cannot be relied upon, providing a stable supply. So, for example, we have solar light, but we don't have the solar light in the night time. So, if you need to have the power whole day and night, you cannot rely upon the solar power only because in the sunny day, it will provide a lot of power, but in a night time or a weather where sun is not visible or a rainy weather, your energy production will be very less. So basically, you have the supply, but you need a power storage that is called a battery. You need a battery required in between your power consumption and power consumption and your power generation. So when you have the power at the daytime, you will directly take from sun, and we have excess power which will be stored in battery. And when you require in night, you can take from the night. So similar happens with the wind energy. If you have a day where velocity of winds are very high, then you will get excess energy. But when you have the wind energy lower, then your energy production will be lower. So this intermittent nature, it is always there with wind and solar energy sources. The fourth option is of the same value at the same time of each day and given location. That is incorrect because we will not have the same values at the same time for any given location. But it depends on the uh, location, time, day, and the time of the day. So option fourth is incorrect. Then it comes at the sixth question. The electrochemical devices can be used to store. So these are the electrochemical devices. Electrochemical devices mean they can store the electricity in terms of chemical or electrochemical reactions. So these are electrochemical devices, battery, electrochemical, fuel cells, supercapacitors. So these are electrochemical devices. So they cannot generate energy, but they will store, and they will, whenever required, they will generate, they will just provide back. So they are energy storage. So electrochemical can be used to store wind energy, solar energy. So if we have wind energy from windmills, can be if we have the energy excess, we can store in the electrochemical devices, or let's say in batteries. Similar for the solar, mechanical energy as chemical energy. Yes, that is also correct, but not the heat energy directly at heat, because electrochemical devices, they can only store the energy in form of chemical reactions. So they cannot store directly as heat. So option third is incorrect, but option 1, 2, 4 is correct.
Sir, one query, sir. Sir, regarding sixth question, please.
Yes.
The electrochemical
Hmm.
is not electromechanical, sir, because the wind energy, there's no chemical part, no, only
Yeah. So it is not mechanical. So option 4 says the mechanical energy as chemical energy. So they have specified, because they cannot stored in mechanical form. But let's say you have some moving turbines. So you have some mechanical energy. So you need to convert it in some way as chemical energy. Then only it can be stored in electrochemical devices. Otherwise, it cannot be. The mechanical energy cannot be directly stored. So that is why they have specified as chemical energy. Similarly, we are seeing the wind energy and solar energy. They just sorry, wind energy first it will be converted to electricity, and then it will be stored. Not directly wind, because wind energy is not a quantifiable thing to store in electrochemical devices. So option 3 is very much incorrect, because they are saying that it is directly as heat stored in electrochemical devices. So that is why we are saying that option 3 is incorrect.
means they are asking about the storing, not about the generating the.
Not about the generation. They are just asking the electrochemical devices can be used to store. So we just need to compare in which way we can store in electrochemical devices.
A different type of energy.
Yes.
Okay, sir.
So the question says it is from the previous quiz questions. So I guess they can from the previous lectures. Yes, this was from the previous lecture. So let's just finish it up. So which sector shows the largest energy consumption pattern? So residential, transportation, industry, and transportation related to residents. So we have this pie chart we saw in this previous class, week 2 classes, that the industrial has the most significant contribution of global energy demand. So similarly, we have the largest energy consumption in this In these four options, the industries have the largest contribution for energy consumption. So the industry is correct here. Then we see India and China have more renewable energy sources than other countries. So more scope of automotive industries to grow, lower GDP than most countries, and lowest energy usage in transportation compared to other countries. So option one, we cannot say directly that India and China have more renewable energy sources to other, let's say comparing solar energy and wind energy. So we cannot claim that we have more solar energy than other countries, or China have more energy, more solar energy than other countries. So the statement one cannot be true. And let's take the third and fourth first. So lower GDP than most countries. So we are not very low. So China is itself having a very high GDP, and India is also having good GDP. So we can say that statement three is correct. Then fourth is lower energy usage in transportation compared to other countries. Lower energy usage in transportation. So that is also not correct, because we are having the same energy usage in transportation, more or less same compared to other countries. We don't have the lowest energy uses. We can say we are at the lowest level. So option two is more scope for automotive industries to grow. So this option is yes, it is correct, because the automotives is directly related to the population, and India itself is as a very growing country at a very high scale, at a very fast scale. So the automotive industry is also growing very fast in India and China, countries like us. So the option two is correct, that we have the scope of automotive industry, but we cannot claim all three other options. Then we have this is question from the previous class, and this was from the graded questions of previous class. So the cleanliness of which fuel is burned inside an engine is decided by which ratio? So I explained it earlier also. So what is the internal combustion engine and the process inside the engine? So we have a fuel, which is basically a hydrocarbon. So we have, let's say, methane or CH4, and we have oxygen here. So then it will come react in between. So we have one carbon, four hydrogen, and let's say four oxygen. So it will, during the combustion, it will compressed, and the one spark will be there, and then they will react with each other. And what we have in the product, we have the water as H2O and carbon dioxide as product, and some heat which will drive our automotives. So that heat is basically, or this energy is basically what will we get in internal combustion engine. So we see that if we have a proper ratio of 1 by 1, then whole the reactants will convert in the product as water and carbon dioxide. So that will be a perfect combination for the combustion. If we have more fuel, less oxygen, or less air, then we will have having excess fuel in at the product side. So that will not be clean enough. And if we have more air, then also we will not have the perfect combination of this ratio, and we will see that the engine is less efficient. So basically, we should have a proper fuel to air ratio. That is why in our automotive, in our cars or bikes, the ratio is perfectly tuned. So we need to perfectly tune the ratio of fuel and air. If one of them is lower, then we will not have the proper combustion and proper functioning of the engine. So the option third is correct, that yes, fuel air ratio is very important and should be decided by the uh, it decides the cleanliness of the fuel burn inside the auto engine. So this is the last question of our discussion for today. So the industrial sector uses maximum energy for generating electricity, which each industry air conditioning, process heating, lighting. So it is also from our previous class. So in the previous class, we saw that what is basically process heating. So process heating in the any industry, whatever process require high temperature. Let's say when we need steam, warm water, hot water. So these kind of all activities comes in process heating. So what for basic fuels required are natural gases, coals, petroleum, or the fossil fuel based product. For now, industry are using mainly the first fuel as these non-conventional these conventional sources. Then why we are focusing on the process heating? So we can see the industry accounts for 25% of this EU final energy demand, and of the total industry energy demand, process heating consumes 90-20 terawatt hours, or it is around 60% of total energy consumption by the industry. So we can see this is the process heating is a very uh, large portion, taking large portion of the energy consumption of any industry. So yes, we can also see in this, for example, of a dairy product. So in this case, most of the energy is required in sterilization, spray drying. So these are happening at the higher temperature. So whatever happening at the higher than the room temperature needs the process heating. So that is why process heating has a major contribution in energy consumption. So the answer to the question is the process heating. So okay, for now we have done the all the assignments for today, and we have discussed the lecture content of week 3. So now we have time for let's say 15 minutes time for interaction and discussion. So if any one of you have any questions regarding the today's lectures or the previous lecture, or anything else related to the academic things, so you can ask me here. I will be here for let's say 15 minutes till our till 9 p.m. So you are free to ask. Otherwise, if you don't have any question, you are free to leave, and you may leave if you don't have any queries. So for your information, all the lecture slides are available on a Google Drive, which the links will be provided, I guess. Otherwise, you can ask me the link. So all the lecture slides are available there, and the lecture videos are available on the YouTube. So YouTube channel link you will also get from the NPTEL. Otherwise, you can ask me anytime, and you can also ask your question there. So I will reply back to you whatever questions or queries you have. So okay, thank you for today. So if you have any queries, you can ask.
सर थैंक यू सर सर एक क्वेश्चन था
Yeah.
सर
हाँ जी.
ये सब्जेक्ट का नहीं है सर सर मैं
हम्म,
वीक 1 2 का थोड़ा लेट स्टार्ट किया है सर चलेगा
हम्म.
सर मतलब हफ्ते में कवर अप कर लेगा सर मैं
That is not a problem. So these are available online, so you can cover up is according to your time. So
ओके
that is
सर
okay.
एंड
Yeah.
क्वेश्चनर इज वी कैन अटेंड आल्सो नाउ आल्सो राइट सर because already week 4 started sir it's
Yes, yes. You can attend according to your convenience. So that is okay.
okay sir
Sir,
okay sir
please email ID you.
My email ID. This is my email ID as well as my LinkedIn profile. So you can contact me here also.
Yes, sir.
So if you have any confusion, this is 0, not O. So it is Lalit
sir
Bharti 0@gmail.com.
सर और एक जनरल क्वेश्चन था सर सर ये प्राइम मिनिस्टर रिसर्च फेलो मतलब क्या है सर वो थोड़ा
Yeah. So that is basically a specific scheme for PhD scholars. So let's say if you are doing PhD in premier institutes like IITs, ISC, few NITs, and few top central universities. So this is a scheme specifically for this institute. So you need to apply for it. So there are different ways to apply: direct entry, lateral entry. So if you got selected, so you comes in a PMRF as a PMRF fellow. So similar to NET or GATE, similar to your NET fellowship, you get a fellowship. So this fellowship is higher in case of PMRF. So we get around double of the fellowship as a regular compared to regular fellow. So, but you need to be in the in these fixed institutes, so selective institutes.
The selection based on the gate score or interview
No,
basis.
no. So what happens? There are two ways. First is the direct entry. Second is the lateral entry. So for direct entry, what you need, you have to be in, let's say in IIT for your master's or your bachelor's. Let's say you're doing a MTech course. So you can apply directly from IIT and while joining your PhD. Otherwise, if you are not from these institutes, so what you can do, you can start your PhD in some of any of these institutes. Let's say IIT Kharagpur, you can start your PhD, and they will call in twice in a year. So when the call comes, you can submit your application. So there's a process. You need to provide your CV, your proposal, your application, whatever all other requirements are there. So then they will select according to whatever criteria they have. So this is the lateral entry. For direct entry, you need to already be registered in a PMRF eligible institute. Let's say in IIT Kharagpur, then you can directly apply for PhD in this under this scheme. So if you gets this fellowship, then you can directly be a PMRF fellow.
Okay, sir.
So am I clear to you?
Yes,
So
sir.
what you are doing right now? May I may you introduce yourself?
Yes, sir. Sir, myself, Sharan Basappa Vijay Kumar Chikkopa, sir, from Karnataka. Hello, sir.
Yes, yes.
Yes, sir. My from Karnataka, I'm speaking, sir. I'm working for Reliance Industries Geo
Mm.
as in Raichur district and Yadgiri district. I'm looking for two districts, sir. Why
Okay.
I choose this course means, sir, in Karnataka, Bidar, we had Reliance biggest solar plant they have deployed, sir. I tried to move internally, but did not allow. So I thought to take course then and apply for management, asking for. I did my course, so chances will be high to
Oh,
move there, sir.
yes, yes, yes. So at what position you have right now?
I'm in lead position, sir. Like manager position is there.
Okay, okay. Okay. So it is technical
For
or
telecom,
administrative positions?
no, it's in manager. Technical, I was last year. I was in technical, like utility and the fiber department. I was looking. So last 1 year, I got promoted, sir. So now I'm looking in utility, RF, fiber, ISP, all five domains of Reliance Geo in two districts. I'm looking, sir.
Okay. Yeah, good. So the PMRF fellow, it is the course, the when we are doing the TA fellowship here, just yes, we are teaching here. So it is part of our PMRF fellowship. So our aim is to aware people about the this fellowship or the research going on in premier institutes. So this is the online way to convey our message. Otherwise, we also take classes in offline to students and convey how can you be a PMRF fellow and how can you go in this field. So one of the motivation is you get the fellow very good decent fellowship of let's say in initial year you will get 75,000 per month and it goes up to 85,000 sorry 80,000 per month. in this PMRF under scheme. Otherwise, usually it is 30, 35, 40K. And in the PMRF 2.0, it is expected to go as around 1 lakh per month. So it is, this course is also for motivating students and motivating other academicians to involve in research. And you can also apply for, you either you or any none of you can apply for this scheme. So you can go into the research field.
Thank
Sure,
you,
sir.
sir, for sharing the knowledge regarding PMRF. This is very
Yeah.
good.
Yes, yes. So this is the special uh, special scheme, you can say. So it is started from around 2016, and one phase is finished by this year. So almost 11 cycles, I guess, 11 or 12 cycles. And now government is starting the phase two. So it will start by the next session, I guess. So now they are starting it. So this was basically the motivation was to the students from IITs, ISCs who are after the graduation or after their masters, who are going abroad for PhD. So because the bright minds of or the top-notch students will go to abroad because they have a better lifestyle there, better fellowships there, better facilities there. So just to capture those students and keep them in India itself. So that is why this was the one of the motivation of this scheme. So this is a very good scheme of government of India for. So this is the highest fellowship, you can say, for research in India. Yeah.
Sure, sir. Hello, sir.
Yes, sir. Yes.
Sir, may I have one more minute of you, sir. Sir, initially when course started, very few members were there. I
Mm.
thought maybe we'll cancel, or maybe this course will be not much attractive
Mhm.
as maybe less members are. But
Mhm.
as total, sir, I can say like 1 hour 52 minutes I spent. I felt like
Mhm.
even though if 1,000 people were there, I would get the same kind of knowledge. I thought I felt, sir, at the last. Initially,
Yes.
because I used to take online classes in, I don't want to name some universities. They used to
Mhm.
cancel the session. No, but
Oh,
you are one motivation, sir, for us. Like even though we were very less people, you give the classes like as if like 1,000 people are listening. Like that, you give the knowledge for us, sir.
yeah. Thank you for this appreciation. So my motive here is if even a single person, or even let's say, because I will tell you the case at the first week one. So what happened? The link given by me was having some issues, so nobody could join at the first week. So
Yes, sir.
Yes,
I
I
wait.
was
I did.
connected. It was fine, but I
Yes,
could
yes.
not.
So I did wait for some time, but I got to know that the link is having some issues. But since we have the facility of the uploading the videos on YouTube, so I recorded the whole lecture alone, and I just uploaded the lecture on the YouTube. So anyone can go to the YouTube back and just see the lecture normally as you are seeing. Just we can don't have the interaction there, but yeah, it is uploaded there. So motivation is again the same. If 1%, 2%, or even no person is there, but they may go to the YouTube lecture. Let's say they don't have the proper time, or the timings are not in their favor, but they can go to YouTube anytime and they can see the lectures. So that is the main motivation. And this course itself, having a lot of students, like last I took this course even last year. So last year 7,000 students were enrolled in this course, and we had three people interacting in last year, and this time only I am interacting with the students, so that is okay. And I guess around similar number of 7,000 or higher number are enrolled in this course in this time, because this is a very versatile course, and people from industry can be benefited, and people from academics, even from the graduation level to PhD level, so that they can be they can take this course. In last course we had interaction with few people. So one was from assistant professor in Galgotia University, Noida, and one was working in some solar plant. And as you told, you are working in with Reliance.
Right now,
So
I am regular from Galgotia University. Myself
yeah,
regular.
yeah, yeah, yes, you are
Yes.
here. So actually, I can't see your faces, so because my screen is continuously on this PPT, so I can't see who is present. But yeah, I remember you. So
Sir,
one thing I request you, so you can also connect with me on LinkedIn. So I am quite active on LinkedIn, so it will be helpful for me also. So if you can connect me with LinkedIn, so you can just search my name. If you search my name, Lalit Bharti, you will see this profile and the Prime Minister Research Fellow, the
sure,
IIT
sure.
Kharagpur. So you can connect me there, and that will be good for both of us.
Yeah, sure, sir. Sir, your research work in renewable energy resources.
Yes, my research is on focusing on batteries. So we are focusing on batteries beyond lithium ion. So what you see nowadays, it is prominently it is dominated by lithium ion technology. So lithium itself having many issues. So first is the resources itself. We don't have the lithium resources in India, and we are relying on the countries like China and other. So we are taking looking at the substitute of lithium ion. So in this case, we are working on sodium ion batteries and upcoming new in chemistries, let's say aluminum ion battery, potassium ion battery, even some zinc ion batteries. So my work is basically on beyond lithium ion battery system. So we make different type of batteries and try to do something. So this is my research field mainly.
Okay, sir.
So you are also doing any research projects in Galgotia University, or you are just teaching as assistant professor?
Actually, sir, presently I am pursuing PhD from NIT Patna, National Institute of Technology
Okay.
Patna.
Yes, yes, yes.
Yes, and I am interested electric vehicles. My background is electrical engineering.
Okay, okay.
That's why people ask, yes, you are working about the battery management, yeah, battery controlling, there's a lot of things. So that's why I'm asking, I ask you on which part you are working. Told you a
Yes.
battery. So I'm
Yeah.
interested in electric vehicles. Yeah,
Mhm. Yeah, we recently submitted a patent on sodium ion based electric bicycle. So that was also in media, and a lot of things were happened according to that. So we went to DST head office in New Delhi, and
really, yes, yes.
uh, so we took our bicycles there, and the chairperson, the secretary of DST. So he's, I guess, uh, there's new secretary now. So, but I don't remember the name. But the secretary of DST, they integrated the electric cycle there, and we had a function there. So the similar thing is got patented here. So we have submitted the patent, and we are also working close with the industries, some new companies, some new startups. So we are also looking in that aspect of industry to commercialize the sodium ion batteries and new batteries. So
Sir,
lot of work is.
yeah, yeah. I have visited many industries in Noida and Greater Noida, Ghaziabad.
Mhm.
So what they are doing, they are just assembling, not manufacturing.
Yes. So the main issue
They
is
are saying
there.
that,
Even if you are
yes,
saying you are having Ola bike, let's say.
yeah,
So
yeah,
they are for Ola, I guess they are manufacturing some batteries, but most of the batteries are again imported by from China. So what they will do,
And
they will just import the cylindrical cells, they will just assemble here and they will make their own battery. So
one more problems happens so that they have just imported batteries and assembled and given to dealers.
Sir, sir. Sir, I work on this lithium-ion battery, sir. Daily I come across. Usually
so
this cells imported. Then for telecom we use those cells, sir. So whenever there is a
Yes, yes,
faulty, we that particular cell and we replace it locally. But companies like Costlight, Vision, Exicom, we are using here, sir. Like in north part of India, they are using Philips.
yes, yes, yes. So because for at the commercial at the industrial level, very few companies have their own plant from for end-to-end product. So Ola recently, yes, I guess Ola recently they inaugurated their plant. So they are from raw material to battery manufacturing. They are doing at their own, but it is not for all the batteries they are using. So, but they started the plant. So it was the first plant, and Reliance is following, and some other companies are following. But even at today's time, we don't have the proper production of batteries here. So that is why this e-vehicle sector is more hazardous for India, because let's say for automotives, India is the biggest one of the biggest manufacturer of automotives. So let's say bike, motorcycles, we are manufacturing and exporting to other nations. So most of the parts are manufactured in here in India, in country itself. But what happens in e-vehicles? So most of the parts are important. Let's say if you have good quality motor, the motor itself important, the batteries are itself imported, then just we are just assembling, and most of the part is either Chinese or something else. So that is why the
yes,
need of our indigenous batteries come. So we need to either make our own lithium ion batteries, or if we don't have the cheap lithium, then we need to go to sodium ion batteries, some other type of batteries. So in that perspective, we can be self-reliant. So that is the main motive of that work.
yes.
So
Recently,
this,
IEEE conference, UP section, and Dr. S. N. Singh, society in Gwalior, and one professor from BHU, IIT BHU. They have discussed a lot of things. And the,
do you remember the name of the professor?
yeah, Dr. R.K. Singh from IIT
Yes. Yes,
BHU.
yes, yes. No, I know
I
them.
think, yeah, he was working in electric vehicles, and yes. And one professor, Dr. S. N. Singh, is a IIT Kanpur.
Oh,
But
yes.
right now he's working as a director for IIT in Gwalior, MP.
So for the IIT sorry, this BHU thing, the
Yeah,
Professor R.K. Singh is our close collaborator,
yeah,
and
yeah. Keynote
recently we had a conference in Banaras, and fortunately I got a best presentation award also in that conference. So we
great.
recently visited BHU.
Yeah, yeah. Actually, recently, 2 days before, IEEE conference, and they have given a keynote.
Yes, yes.
Yes, sir.
So we are also having our conferences here. So one conference is going to be happen soon in May in Kolkata. So this
Okay.
conference is focusing the industry. So it will be a short conference. So our industry MOU partner is also uh, launching their own homemade, or sorry, these self-made sodium-ion batteries. So they are launching their batteries in their conference, and as well as some industries will participate. And at the end of this year, around in November, we will have a academic conference. So in that, industries as well as the academicians will take part. So it will be, I guess, it will happen in IIT Kharagpur itself, otherwise in Kolkata. So you can also, as a industry partner, also you can take part of that because they will share their experience, then how the industries are thinking about the energy sector in India. So that is also helpful for industrial people as well as for the academic people.
Yes, sure, sure.
So I request to just make connections over
Yes,
LinkedIn. So
sure, sir.
there is,
After
yeah,
completing
sure,
this conversation, we will connect.
yeah, sure.
So, I will send a
Sure.
mail from
No,
my side.
no problem, no problem.
Nice to interact with you, sir, because uh, can't discuss all things by looking YouTube lecture. Here we can discuss our problems and what is going on.
Yes, so actually what happened, the course is slightly modified here, because modified in the sense, last year we don't have such students to interact. So this 2 hour time was a lot. So what I did, I just started teaching from the this PDFs, the lectures PDF notes, then started the assignment part. So, but now we are having so many, you are interacting a lot. So we can just skip some of the part and we can make more time for discussion. So it is up to us. But this time
Yes,
we are getting a good audience, you can say. So I am getting a good lot of interaction. Or last year, otherwise I was just doing my presentation, then I was waiting for anyone who will interact, but nobody was interacting last year. So
no, sir, I am interested because really,
sure. So we, what we'll
thank
do
you.
for next time,
Great,
we'll try
yeah,
to have more time for interaction.
yes, 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 sir.
So I will try to cover up my my presentation slides as soon as possible. Then we have more than half an hour, let's say more than 45 minutes to discussion on this course.
Yes, sure, sir. Thank you, sir, so much.
Sure.
And
Yeah,
good
sure.
night.
Thank
Sure,
you.
sir. Thank you.
Okay,
Thank you, sir. Good
let's
night.
so let me wrap up the session for today. So hope to see you in next week, and we will have the week 4 content of the course, and we will have further discussion on the course. So thank you all and have a good night.
Sure,
Thank
sir.
you, sir.
Thank you, sir.